in an experiment.
We don't know yet.
Why is light so far?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This week, how the Great Fear spread through 18th century France.
And what quantum interpretation are you? I'm Nick Petrichel.
And I'm Benjamin Thompson. The Great Fear was a short period in history around the start of the French Revolution, where rumours spread about an aristocratic famine plot to starve rebelling peasants into submission. In response, a panic spread, and manor houses were attacked. Exactly what caused this, though, has been a matter of debate. Now, a new investigation using epidemiology may offer some clues. Reporter Jeff Marsh has the story.
When social protests like the Arab Spring that erupted in late 2010 reach a critical point, they can spread like a virus, and once they get going, they're very difficult to contain. A lot's been made of the role of social media in these and similar modern-day protests, giving ordinary citizens essentially limitless reach to share their grievances. But uprisings have ignited long before our social connections went digital.
So the Great Fear is a wave of unrest and riot that happened in France at the beginning of the French Revolution. And this often started as a result of rumours. So rumours were spread through the country saying that there were bandits that were trying to attack the city or the village. The spreading of this fear went all around France, from peasant to the more advanced bourgeoisie. So everybody was somehow part of this unrest. And then as a result of that, people would organize themselves for militias, and sometimes and quite often the people, they assaulted castles. They burned sometimes castles. So there was sort of unrest throughout the country. That was spreading, because then these messages about bandits would go from city to city, from village to village, from town to town.
If you could just please introduce yourself.
So I'm Stefano Zapperi. I am professor of theoretical physics at the University of Milan. I'm an expert in complex systems, statistical physics, and I work on many fields using my expertise with data and with modeling. Epidemiology tells us how disease spread from place to place and from people to people. So we thought that it was very similar in spirit. And we could use models that tell us how, for instance, a disease would spread from one region to another, and applied to the spread of rumors. Although nobody was really getting sick, but people were getting infected in the sense that they would start to feel these rumors and act in accordance with it.
On the off chance that a recap's helpful here, yes, this is an Italian theoretical physicist investigating French political history using tools from epidemiology. But please do hang on in there, because it will make sense.
You know, French Revolution is a very well-studied period, so everything that was there has been recorded by someone and then maybe written up by some historians, even at the time. So we have really a huge amount of information that has been written and recorded and transmitted. And actually, there is a great French historian, Georges Lefebvre. In 1932, he wrote a book, it's called The Great Fear, where he collected all this information from the historical sources. So he could say, for instance, that in a certain town, on a certain date, there was a rumor coming as a letter from another town. So we have a very good picture, but of course the information is scattered. So our job was to put it into the same framework and to digitize all this information that is there and has been recorded already almost 100 years ago by historians. So we have two main competing theories that have been developed over the centuries about the Great Fear. So the first was advocated again by Georges Lefebvre, who said that the Great Fear was really a political event, so was part of the revolution, and the idea of bandits spreading fear was just a pretext to revolutionary events and revolts and riots that had a political aim. The second interpretation, more modern, was that the Great Fear was an irrational event that had no real meaning, was just driven by emotions. And these emotions were spreading, and this created all these riots. But they had nothing really to do with the French Revolution. It was more an epiphenomenon, something that happened on the side. Our aim was to understand which of the two prevailing theories were right, and do that with tools of epidemiology. So at the beginning of the study, we had a set of dates and places where the Great Fear was recorded. So we created a data set that has all this information encoded in a digital format. And on the other hand, we had a map of roads of the time, the so-called Cassini map, compiled in the 18th century. And recently, some researchers had digitized this map. And then we could make the merging of the two datasets and try to understand which particular road was taken by the Great Fear, so by the rumours. So it's not only from which town to what town, but also through which road. So we could see really how the spread was going in time and in space through France. So we could literally watch three waves coming from different locations and then merging together at the end in the south of France. And we could also measure the speed that was several kilometers per day, that was compatible with the typical speed of men walking sometimes, and some other times even faster, like a carriage or a horse running at full speed through the roads. So the map we constructed tells us about the when things happen and where things happen, but didn't tell us anything about why things happened. So we wanted to understand this better, and we tried to see which factors were driving the spread. So there were some towns that were not affected, some towns that were affected, and we wanted to understand what distinguished them. In epidemiology, that would be computing risk factors for disease, while here it would be the socioeconomic factors that would make a certain region more prone to the spread of the Great Fear. So we studied all possible socioeconomic factors that we thought were relevant, starting from the price of wheat, which is well known to be a driving factor in the French Revolution, the legal systems concerning the ownership of land, the population, so which towns were larger and which towns were smaller, literacy rates, so how many people could read and write, and finally the income, so how many people were rich and how many were poor in that particular town or village. We found that larger towns were more prone to the spread than smaller towns. This is similar to infectious disease, where of course big cities are hubs for the spread of the disease, while small towns are affected later and sometimes never. Then we looked at the price of wheat, and we found that cities where the price of wheat was higher were more likely to be affected by the Great Fear than cities where the price was lower. Yeah, an interesting factor was the legal system, and this was especially the system that ruled the free ownership of land. So you have to understand that in a feudal system, the land belongs to the lord, and so nobody can own land. But there were different rights in different regions allowing people to own land. And we found that the fear was more prevalent in regions where the ownership of land was linked to a physical title that stated that the lord owned the land. So in areas where you could destroy the right of the lord, the Great Fear was more prevalent than in regions where the rights were given to the lord no matter what. We also looked at literacy rate and income, and we found that richer and more educated towns were more likely to have experienced the Great Fear. Finally, we looked at what stopped the Great Fear. And what we found is that an important event, 4th of August, the abolition of feudal rights and privileges, played an important role. The hypothesis is that once the goal were reached, so the abolition of feudal rights, the fear had no reason to spread. So taking all the evidence together, our work supports the hypothesis put forward first by Lefebvre already almost 100 years ago, that the Great Fear was a rational event driven by revolutionary ideas and not just an irrational event driven by emotions.
If messages could spread around 18th century France like a pathogen and be of such political consequence, what does that mean for our modern, highly interconnected world? With no shortage of inequality and perceived injustice, why aren't we in a constant state of political revolution?
So today, rumors and information can spread very fast at the speed of light, and we can have online chat and a discussion over the internet and rumors spreading very fast. But in order to act on it and to do something like a riot or some event, you need a physical space. So people have to meet, and you cannot have a riot online. So even in French riot 20 years ago, researchers could see that the geographical proximity was playing an important role in the spread. So you need geographical proximity even today, as it was during revolutionary France.
That was Stefano Zapperi from the University of Milan in Italy. You also heard from Jeff Marsh, who produced this story. To find out more, check out the show notes for some links.
Readers of Nature have been finding out what quantum interpretation best suits them. The results and more from that are coming up. Right now, though, it's time for the research highlights with Dan Fox.
Researchers have proposed an unorthodox origin story for dark energy, namely that it forms in the gravitational collapse that creates black holes. Last year, physicists discovered that dark energy, the unknown force accelerating the expansion of the universe, could be evolving rather than remaining constant as was previously thought. One explanation is that the collapse of mass under gravity when a black hole forms might convert matter into dark energy. Varying black hole activity would then explain how dark energy's density, and so the acceleration of the universe's expansion, changed over time. Researchers analysed how this theory, known as cosmologically coupled black holes, fits with experimental data and found that it tallied with two measurements of the universe's rate of expansion as much as the standard cosmological model does. But unlike the conventional model, this theory allows neutrinos to have a mass that matches with results from laboratory experiments. You don't need to search a black hole for that research, it's in Physical Review letters. A marsupial micropredator native to Australia has overcome near extinction, in part thanks to its resilience during drought. The rat-sized carnivore called the amperta has defied the odds by moving from nationally endangered to of least concern in just 2 decades. To understand how, researchers surveyed signs of the amperta's presence across an arid region of Australia. They found that the amperta's range expanded by almost 50,000 square kilometres, an area bigger than Denmark, between 2015 and 2021, despite a record-setting drought occurring during that period. They report that the main driver of this surprising comeback was a campaign that reduced the number of rabbits in Australia. This in turn caused a drop in the population of non-native cats, which eat rabbits, but also ampertas. The researchers suspect that the amperta's dietary flexibility and ability to enter a state of reduced metabolic activity helped them to bounce back despite the extremely dry conditions and the resulting food shortages. You can read that research in full in Biological Conservation.
As you may be aware, it's quantum mechanics' 100th birthday, and in celebration of that, Nature has been producing a range of content. In a recent feature article, reporter Lizzie Gibney also wanted to know a little bit more about which quantum interpretation suits you all at home best. She joins me now. Lizzie, hi.
Hello, Nick.
Thanks for joining me, Lizzie. So, in your recent feature article, it was all about different interpretations of quantum mechanics. Can you give us like a roundup of those first of all?
So, quantum physics, the mathematics of it, always come up with predictions that everyone can agree on, but the interpretations describes the principles, the assumptions, the what is going on beneath that. And there is a huge range of different interpretations. The Copenhagen interpretation people might have heard of, and that kind of puts a premium on measurement. So we have a bunch of fuzzy probabilities that represent the state of a particle, and then you measure it, and then you have this defined outcome, and it describes measurement as being really important in that process. We have other interpretations such as purely epistemic ones, so they're all about information, and the idea there is the wave function that's describing the state, that is just about making predictions. There is nothing real behind it. It's just a way of kind of betting on a particular outcome. And then we have ones which are at the slightly wilder end of the spectrum to some people, but like it's called many worlds interpretation, where it posits that rather than have this transition from your wave function that describes all the possible states to just one defined outcome, actually what happens is all the outcomes happen just in different universes. And all of these things are mathematically pretty much equivalent and valid. And then so which one an individual physicist thinks is reality is really going on comes down to something else, to some kind of thought process or personal preference.
And so you've already surveyed quantum physicists about which interpretation they prefer, and you got some very different answers. People seem to disagree quite a bit. And now you've done a quiz to, I guess, get a sense of the broader Nature audience, what they think about it. What was the thinking behind this quiz?
So the survey was very precise. The quiz is a lot more fun. We're asking people about their favoured quantum interpretation. So that's, how you view the underlying world behind the equations of quantum physics. And actually, it's kind of based on the assumptions that you make, how you view the world, what you think is important in science and isn't. And so I thought that was something we could translate onto everyday readers, not just quantum physicists, a little bit like when I read my Cosmo magazine as a teenager, the idea of matching up which Spice Girl I might be, depending on answering a few key questions. I wondered if it would be possible to share this quantum fun with all our readers and give them the same type quiz, but to find their quantum interpretation.
And this was a slightly unscientific quiz, but what did you find from it?
Yeah, so this was very much done not in consultation with all the experts who helped me with the survey. But what I found was actually quite surprising. There was quite broad agreement with the survey in some ways. The most traditional interpretation, the Copenhagen interpretation, was also the one that got the largest response in the quiz. And, broadly, I think there was quite a lot of similarity. One general thing I think that we found was that realist interpretations of quantum physics were more popular among our general readers than among the quantum physicists. And, the realist interpretations are saying that when we describe quantum physics, we have this thing called a wave function, which tells us about the state of a particle, that has some kind of correspondence with reality versus, say, an epistemic interpretation, which just said it's about information, it's about making predictions. And it seemed that, in general, our more lay audience, or not quantum physicist audience, wanted an interpretation that was realist to a greater extent than the quantum physicists.
So would you say the people answering the survey, maybe because they know less about quantum physics, they think more that it describes a very real set of things?
Absolutely. It may also be that they don't know as much about the problems that leads to. So the thing with realist theories that they've really struggled with is if what you think is this wave function is something real, and we have this fuzzy probabilities that describe a state, and then you do a measurement and it actually has defined probabilities, something happening instantaneously like that, which is sometimes described as the collapse of the wave function, is very hard to reconcile with physics generally. Like, we have this smooth change that's described by one equation, and suddenly you measure it and it's just something completely different, described in a completely different way, and it's a fixed number. That's a very unusual case, and it really jars with physicists. And there are ways to explain it, but some of them involve, again, an instantaneous influence is something that, if you don't try very hard to sidestep it, can clash with special relativity, which says that, nothing should happen faster than the speed of light. I mean, instantaneous, that would be faster than the speed of light. And there are, again, ways around it. For instance, conjuring all of these many worlds. Lots of people, for some good reasons, are not happy with that either. So the realist idea seems very, very appealing, I would say, on an intuitive level. But I think maybe quantum physicists themselves know that also, unfortunately, comes with quite a lot of baggage. And so many more, perhaps quite sensibly, say, well, we're going to look at it in this slightly different way, which may strike the layperson as very odd and unsatisfying, but actually for them might be the most satisfying.
And do you think this quiz, as unscientific as it is, can tell us anything about how we talk about quantum mechanics, or perhaps how we present it to a broader, high class, but more everyday audience than quantum physicists themselves? Well,
I didn't think it would be possible. So I wanted to do this, and I had this idea, like a kind of choose your own adventure type. I wanted something of that flavour, but about quantum interpretations. And I didn't really know if it would be possible, because you have to kind of do yourself a little logic puzzle of which different interpretation fits with which different question, and then you put it all in an order to come up with your logic. And again, this was also limited. I picked just like 5 of the most prominent. I didn't go into some of the interpretations which have smaller followings. But actually, the fact that it was possible, I do think is kind of interesting, because then maybe it'd be a good starter point for people who are studying quantum foundations would be to ask themselves these questions, because it maybe helps get at your own, dare I say, prejudices or your instincts, which maybe it's good to be aware of once you start applying this and trying to actually study it in great detail.
And which quantum interpretation were you?
Well, oh God. So when I do the quiz, I came out with the one that says there's no good interpretation for you, because there was that option.
You're special.
Yeah, well, there were quite a few people. So on 2 different paths, one path had 14% of responses, and that was there's no suitable theory for you, and that's for people who wanted a theory to be local, which means that we can't have some kind of at a distance influence. And then 3% was the people who also had no suitable theory, but they were happy with this kind of what we call non-locality. The idea that there can be some kind of influence that happens across a distance. So in physics, things can happen just by immediate cause and effect. Things are next to each other, but non-locality is that there can be something much more distant that is some kind of effect, and it's very hard to understand and explain. So that's quite a lot of people. That's 17% there was no suitable theory for. So I'm with them. And I also tried to say that I think Einstein may have been in one of those camps.
Oh, really?
Yeah, well, he struggled with non-locality, and he also wanted a realist theory. He died before many worlds was introduced, so who knows what he would have made of that. But, there was a tension there between relativity and quantum theory that I think some people who agreed with me may have also answered.
And so if we want to take one thing away from your survey that you did of the quantum physicists and now this quiz, what would be that thing that we'll take away from it all?
I think this really shines a light on the idea that your instincts and beliefs and how you view the world can really shape your scientific perspective. And I know everyone wants to be objective, but it's something, we have to, philosophize about. And that involves bringing different kind of measures to science, looking at it through a different lens and looking at what's important in different ways and inspecting our own prejudices. And I think the very fact that we can do this quiz at all tells us how much our physics and the way we look at physics is shaped by ourselves and, which interpretation or Spice Girl we are.
Lizzie, thank you so much for joining me.
Thank you.
Nature's Lizzie Gibney there. For more on that story, check out the show notes for some links.
And that's all for this week. But if you'd like to stay in touch with us, you can. We're at Nature Podcast on X and Blue Sky. Or you can email podcast@nature.com. I'm Benjamin Thompson.
And I'm Nick Petrichel. Thanks for listening.